Hello, we are in section 8.7 where we're looking at the impulse function, also known as the delta function. All right, the impulse function. So let's start off with the unit impulse. And well, before we do this mathematically, let's think about this, how this applies in physics. We often do differential equations, at least the second order stuff, when we're looking at an oscillating spring and we have an external force, like a forcing function that's controlling the spring. What you can do is you can have a hammer and hit that spring and so it'll have a big shock impulse at that one point in time. Another example would be if you're using differential equations in a circuit, and then all of a sudden you get this power surge. So you get this huge amount of energy going right into your circuit at one point in time, and then it stops. And so that's another example of using this impulse function, or the delta function. All right, mathematically, let's try to define it with a unit impulse function. And the unit impulse function says that if you have a graph, and this is some t naught over here, from 0 to t naught minus a, so some a distance a little bit to the left of that, and then another a distance a little bit to the right of that. So all this time here, your graph will be equal to 0. And then from t naught minus a to t naught plus a, you have a 1/2 of a. So this will essentially guarantee an area of 1. And that's what we want. We want the area of 1. And so this is the property that this has. So if your A changes, let's say your A changes and gets a little bit smaller, then your height will have to go up a little bit higher, right? And then if your area gets smaller still, and then your height will also get higher. And the whole point here is that we want to keep the area under this rectangle to be equal to 1. So the smaller your base goes, the taller your height is going to go. Now, if we let our base eventually get smaller and smaller to infinity, then at that exact one point, you're going to have an infinite height. It's kind of weird. Again, mathematically, it's kind of hard to describe, but it happens so much in physics that they decided to build the mathematics around this idea. So the idea is that it's going to be 0 everywhere except for this one single point. And that one single point, then you have something that just goes on forever. And this kind of helps guarantee that the area under, quote, under this curve is still going to be equal to 1. That's the thought anyways. Mathematically, it's hard to believe, but then again, we've run into a lot of mathematical paradoxes throughout our calculus career. So that's it. All right, so what's the beauty of this is that now we can describe this mathematically, and now we can, Laplace transform is a perfect tool for something like this, a scenario like this happening in a real life situation. We can deal with it mathematically, and we can deal with it using Laplace transforms. It turns out, we're not going to prove it, but you can yourself, if you want to give this a try, run it through the Laplace transform integral. And you'll see that the Laplace transform of the delta function, we're the delta function now, not the impulse, then not the unit impulse function, but the actual delta function. That has a transformation of e to the negative s times t naught for whatever value of t naught this is. Okay? And if t naught is equal to 0, then your Laplace transform is equal to 1 exactly. And you can see this by putting 0 in for t naught into this equation, into this formula, then you're going to get 1. All right, that is our delta function. So let's see our delta function at work in an example of a differential equation. So here is a simple first order linear differential equation, and I think we're ready to go and Laplace transform. This is the first derivative. If you remember, the first derivative is just s times y minus y of 0. And then you have y, a plus y there, and then equal to the delta function. So this has a t-naught of 1. So this is going to be e to the negative s times 1. So that's just essentially e to the negative s. Now remember, a delta function makes that shift in the real world, and a shift in the real world means an exponential function in the Laplace world. And this is what we have. All right, y of 0 is equal to 2. Let's put the y's together. That's s plus 1 times y. And then this is equal to 2 here. I will bring that to the other side. So this will be positive 2 plus e to the negative s. So you can see that shift is at 1, right, when we bring it back. So both of these things, we have y, both of these will have an s plus 1 denominator. So that's 2 over s plus 1, and I'll keep this as a 1 over s plus 1 with an e to the negative s here, and I think we're ready to transform this back to the real world. Transform back, we have y. This is 2 constant, and this is a shift of negative t, not a shift, sorry, this is just an e to the negative t. Technically it is a shift happening in the in the real world, in the Laplace world, and so that's an exponential in the real world, but we don't need to look at it like that. And this next one is a shift happening in the real world because we have an exponential in the Laplace world. So this is going to be an e to the negative t again, but there's a shift, right? So we're going to multiply this by u of t minus 1, and that's the minus 1 shift here. And so this is also t minus 1. All right, we can simplify that and work it out or whatever, but that is your solution. All right, let's do a couple more examples. Here's an example where we have y double prime plus 4y equals to the delta function at pi, 2 pi. All right, so let's do the Laplace transform to the Laplace world. This is s squared y minus s y of 0 minus y prime of 0 plus 4y is equal to, now this is your delta, e to the negative s times pi, or times 2 pi. All right. Well, look nice that this is all, these are all equal to 0 from the initial conditions. And so all we have left is s squared plus 4y, and this is just this. E to the negative 2 pi s. All right, let's solve for y. Just going to be e, oops, this is not equals, this is an arrow, e to the, well, I usually write the function first. So this is going to be 1 over s squared plus 4 e to the negative 2 pi s. So there's going to be a shift, but there's one more thing we need to handle, and this is a 4 here. So this is 2 squared. I think we will need a 2 up in the numerator. You can't just put a 2 there, so you need to multiply this by 1/2. So there's going to be a 1/2 constant coming out. All right, so now I think we're ready to go back to the real world here. Inverse Laplace, and we will have y is equal to, and it's just the one function, I believe. All right, so let's throw the 1/2 out there. So that takes care of that 1/2, and then 2 over s squared plus 4 will give us a sine of 2t. Now remember that there's a shift here, So this shift is going to be t minus 2 pi. So there needs to be a t minus 2 pi shift here. Sine has a period of 2 pi, and you multiply this as 4 pi, so it's going to repeat itself. So I think we can rewrite this as y is equal to 1/2 sine of 2t minus 4 pi. So that takes care of the shift. And then u of t minus 2 pi. I think if you're comfortable with your trig, that's probably okay. Or you can just make sure you look up what happens when you're doing some shifting, because you shift by a period or a multiple of a period, then you're going to get the same function. All right. This one's a little bit more interesting in that it has two delta functions. So let's see how that's going to look like. Laplace world. We're going to have an s squared capital Y minus s y of 0 minus y prime of 0 plus just the y. Now we got a couple of delta functions, so it's going to be e to the negative 2 pi s plus e to the negative 4 pi s. And that's it. Y of 0 is going to be 1. This is going to be 0. So we don't get rid of everything. We get an s there. Let's go ahead and factor out a y, s squared plus 1 times y. And then let's bring this s times 1 to the other side. So that's negative, which becomes a positive s here. And then plus our two exponential functions, which will result in a couple of shifts in the real world when we go back. So all this will have a y equals to, this is an s over s squared plus 1. I think that's a cosine. This is going to be 1 over s squared plus 1 times e to the negative 2 pi s. So that's just the sine function. Another sine function here, s squared plus 1. And this is e to the negative 4 pi s. All right, ready to go back to the real world. Inverse Laplace. Y is equal to cosine of t plus, there's a shift here, sine of t minus 2 pi, u of t minus 2 pi. So this is just sine t, plus sine t minus 4 pi, u of t minus 4 pi. Again, this is sine t. So I suppose we can leave it like that, or we can make it to sine t and then just have the couple of things following it. All right, here's one more. Let's do one more, but you get the gist of it. I think these problems become a little bit easier. The easiest out of the last couple of sections that we've looked at. We had the shift function, or the unit step function, and then the convolution. I think those had some tricky things that you need to remember. But with the delta function, you just have to remember the exponential function in the Laplace world, and then you take it back with a shift in the real world. All right, one more example. I think we're ready to go Laplace world for this. We have s squared capital Y minus s y of 0 minus y prime of 0. That's the second derivative. And then we have a minus 2 times the first derivative. That's s y minus y of 0. And then that's it. Well, and then we have 1. That's 1 over s. And then a shift, e to the negative 2s. All right, let's see. Y of 0 is 0, y of 0 is 0, and this is equal to 1. So there's a negative sign there. Let's be careful with that. Meanwhile, we can factor out the s squared minus 2s y. And then let's bring this let's bring this constant 1 over to the other side. This has a negative 1, it becomes a positive 1, plus 1 over s, plus e to the negative 2s. Oh, 1. We need the, oh no, we're going to divide. So y is equal to 1 over s. We could factor out an s here, right? S minus 2 plus 1 over s squared, s minus 2. Probably could combine that into one fraction. 1 over s minus 2 e to the negative 2s. I think if I combine these two, this will have an s on the numerator and a 1 for the second one. S squared s minus 2 as your denominator, and this was a plus, I believe, 1 over s minus 2 e to the negative 2s. All right, let's call on Wolfram one more time. All right, our first fraction looks like this. I'm going to put the s first. I'll put the 3/4 first because it's positive. So this will become 3 over 4, 1 over s minus 2. That looks like an exponential function. And then I'll go negative 3/4, 1 over s, and then a minus 1/2. 1 over s squared. So this is just going to be a 1, this is going to be a t, this is going to be an exponential. Now, let's quickly do the next one. So the fraction is just going to be a 1 in the numerator, and then an s times s minus 2 in the denominator. And we're going to get 1/2 s, 1/2, well, I'll just write it out here. So these things are going to be with the exponential function, which means it'll transform back with a unit step function. 1/2 1 over s minus 2 minus 1/2 1 over s. And this is e to the negative 2s. All right, I think with that, we should be ready to transform back into the real world where we get y is equal to, this is a 3/4 exponential to t. This is a minus 3/4, just an s, 1 over s, that's just going to be 1. And then this is going to be 1/2 t. And now here's the shift. This is a 1/2 e to the 2t, but there's a shift here, right? T minus 2, so t minus 2 shift, and then I'll multiply outside of this with a unit step function, and then I have a 1/2, and that's just a 1, so I'll just keep it there. There's no variables involved, so the step function t minus 2. All right, okay, and that is your answer. So I think that's good. You can certainly follow these steps through. Just remember that you're getting these exponential functions, and then you should be able to work with that. All right, I hope that helps. Good luck.